This is a video I've wanted to make for a while and I just got around to it. So we're going to look at tensors and tensor products, how they relate to vector spaces, and we're going to make a concrete and explicit construction of the tensor product of two vector spaces. And depending on how well this video does and interest, we may talk about in future videos the relation of our language involving tensors and tensor products and those in other fields of mathematics and physics. So let's set some ground rules or some notation. So for us, we'll use the base field of the real numbers, although we could use the complex numbers or maybe even a finite field if we wanted to. Vector spaces will be denoted by capital letters, generally U, V, and W. Elements of those vector spaces or vectors will be denoted by lowercase letters like U, V, and W. At times, they will be indexed, so like v sub 1, v sub 2, v sub 3, but those will not be entries of the vectors, those will be separate vectors on their own. Generally, scalars will be denoted by a, b, c, or x, y, z. So since we're working over the ground field of the real numbers, these will be real numbers. And then a little bit about me and how I'm approaching this. I'm a pure mathematician. I work in algebra, mostly in the representation theory of infinite dimensional algebras like Lie algebras, vertex operator algebras. And I think it's maybe important to point that out because someone working maybe in algebraic geometry or someone working in differential geometry might have a slightly different take on the notion of tensors. Okay, so let's maybe get started. So the first thing that we're going to form is this thing called the formal product of two vector spaces. And so we're going to say our vector spaces are V and W. We may or may not use the vector space U as we move along. And this formal product will be denoted by V star W. Okay, so what do I mean by that? Well, that's going to be the span, and I guess I should say the span over R. So it's creating a new vector space, and it's going to be the span of symbols little v star little w, where little v comes from big V and little w comes from big W. So it's the span of all symbols of that form. And here's a really important thing, is that there are no relations between these symbols. And we'll see maybe how that's maybe not problematic, but maybe not exactly what we're going for in the end as we move forward with some examples. Okay, so let's look at a very simple example first. And that is, let's take V to be R2. So I'll just take that as two-dimensional column vectors. So I'll denote that by A, B, where A and B are in R. And then let's take W to be equal to R3. So here we'll denote that maybe by X, Y, and Z, where X, Y, and Z are in R. So this is a two-dimensional vector space that clearly has a basis containing two vectors. And this is a three-dimensional vector space that has a basis containing three vectors. Then we have V star W, this formal product between V and W will be the span. Maybe we'll write the R span of everything of the form A, B, star, X, Y, Z. Where here A, B, X, Y, Z are all real numbers. So you might say, well, what's the dimension of this object? Well, we're using the word product here. So perhaps the dimension would be the product 2 times 3. But in fact, the dimension here is not 2. This thing is in fact huge. Its dimension is infinite. And maybe on the next board, we'll look at some objects within this vector space that seem like they should be related, but by the formal construction, they are not related. Okay, so now let's look at some examples of vectors in R2 star R3. So recall that before we labeled R2V and R3W, but now we'll just rewrite it as R2 star R3 just for simplification. So here's one example of an element. We could take the vector 2, 1, and then star it with the vector 5, 10, negative 15, and then maybe subtract 3 times the vector negative 1, 3, starred with the vector 1, 0, 7. Notice that this 2, 1 is a vector in R2. This 5, 10, negative 15 is a vector in R3. So that makes the star of them in R2 star R3. But then this vector is in R2 and this vector is in R3. So then we're taking linear combinations of objects that are built out of things in R2 and R3. So that makes this thing an object in R2 and R3. But notice no simplification can occur here. You might think that we could take this 3 and perform scalar multiplication into this negative 1, 3, but we can't, given the fact that we defined this as the span of those formal products. We're not allowing this scalar multiplication to go inside like that. Then furthermore, you might think, well, we should be able to move this 5, which is clearly a multiple of all 3 of these terms, over to this vector. But again, we can't do that because we define that as a formal product. And furthermore, there's lots of little arithmetic properties that seem like we would like to have them within this structure, but we don't, due to the fact that we formally defined it as that product. So let's maybe give some examples of that. So let's make the heading of this elements of R2 star R3 that are not equal, but they feel like they should be equal. And so maybe our first example will be 2, 4 star 1, 2, 3. So that vector, and 2, 1, 2 star 1, 2, 3. So let's notice that this is 2, 4 star 1, 2, 3, but this is twice 1, 2 star 1, 2, 3. So we don't have a rule yet that would allow us to bring this 2 within this first vector. So a general version of this would be CV star W. So that would be like this guy over here versus CV star W. So given the fact that R2 star R3 is a vector space, we should be able to take scalar multiples of that vector space. And since we define it as the span of a bunch of objects, it's clearly a vector space. Okay, so let's look at another one. Maybe we'll look at 1, 0 star 3, 6, 9 and 3 times 1, 0 star 1, 2, 3. So again, in our formal product of these two vector spaces, these are not the same, but they feel like they should be the same because we could factor a 3 out of every component of this second vector and have it scalar multiply onto the whole object. So like I said, in our formal product, those are not the same, but it seems like they should be the same. So more generally, that would be something like this. V star C times W versus C times V star W. It seems like those kind of things should maybe be equal or at least related in some way to each other. But like I've been saying, in the formal product, they are not equal to each other. Okay, let's look at one more example. Let's say 3, 5 starred with 1, 2, 3 compared with 1, 3 star 1, 2, 3 plus 2, 2 starred with 1, 2, 3. So let's look a little bit more closely at why those seem like they should be related. Well, we've got the same vector in these two spots, 1, 2, 3, as well as right here. And then the vectors that make up the first part of this formal product add to this vector right here. So let's maybe underline those in orange. This is the sum of these two vectors. So if something like this were true, then we would have something like a distributive rule. And we would like to have a distributive rule given that this is like the product of two vector spaces, but we don't in this formal product. So let's say more generally, this is like comparing V1 plus V2 starred with W and V1 starred with W plus V2 starred with W. So again, both of those objects are in R2 star R3, or more generally, V star W, because they're spans of vectors in each vector space. But under our current formal product, these things are not equal. Okay, so as I've pointed out, these are all things that seem like they would be nice if they were true, but are not in our formal product of vector spaces. So let's see what we can do to make them true in what will become our tensor product of vector spaces. So far, we've introduced the notion of the formal product of two vector spaces. And then through some exploration, we saw that that object was really too big, in that it didn't really give us relations between vectors that seem like they should be related. And that brings us to the logical question, how do we create a new vector space, maybe out of that formal product of two vector spaces, so that those conditions are imposed? And the answer is with a quotient vector space. So that means we'll need a subspace of our formal product and then form a quotient with that subspace. So let's consider the following subspace, which I will denote by I. And this is going to be the span of all such vectors in our formal product. So the first one will be CV star W minus C times V star W. So again, we'd like to have some sort of scalar multiplication rule like that hold in our eventual tensor product. It does not in our formal product, but if we put it in the subspace that we quotient out by, then it will occur in our final object. And then we would also like to have something similar happening with the scalar multiplying onto W. So that would look like V star CW minus C V star W. So again, if these are occurring in the subspace which we quotient out by, that means there'll be 0 in the final quotient vector space. Okay, so what else do we want? Well, we'd like something like V1 plus V2 star W to be the same thing as V1 star W plus V2 star W. So that means we'll put the difference of those two in the basis for our subspace. And then we've got one more, and that has to do with a sum and a distributive rule occurring in the second component. So that'll be like V star W1 plus W2 minus V star W1 plus V star W2. Great. Then let's go ahead and point out where all of these parts come from. So here we have C is coming from the real numbers, and then V is coming from V, and that maybe includes V, V1, and V2. And then W is coming from a vector space W, where that also includes W, W1, and W2. And here, V and W are arbitrary vector spaces again. They're not our example, although we will revisit our example. Okay, so now finally, now that we have this subspace, we can form the quotient, which will become the tensor product. So that will be V tensor W will be equal to V star W mod I, where I is this subspace. And in general, we want to write, so we'll have little v tensor W will be defined to be V star W plus I. So in other words, the coset. Okay, so now that we have this construction, let's make sure that it has the right structure. Okay, now that we've done a bunch of construction, let's notice that V tensor W, i.e. V star W mod, that subspace, has nice structure. What do I mean by nice structure? Well, we're trying to build something that looks like taking a product of two vector spaces in a way that it behaves like multiplication. So we should have some sort of distributive rule and other such stuff. So here's an example of that correct structure working, and then I'll leave a couple of other little checks like this to do as homework. So let's notice that CV tensor W. So let's just make sure we know what that means. So C is going to be a real number. V is going to be an element from V, and W must be an element from W. So since V as a vector space has a scalar multiplication rule, that means CV is also a vector from V. So this means that this guy right here is most definitely a vector in V tensor W. Okay, so let's recall that that was defined to be CV star W plus I, in other words, the coset. But now we can extract something from I at no cost, because something from I is deemed as being equal to 0 in the quotient. So let's do that. So we'll have CV star W, and then what can we extract? Well, let's maybe write that in a different color. We have CV star W minus CV star W, and then plus I. And then, like I said, let's point out that this is in I, which means it's equal to 0 in V star W mod I. If you're in I, then in the quotient space, you're equal to 0. Okay, but now we can do a little bit of simplification. Notice that this guy right here will cancel this guy right here, and we're left with the coset C V star W plus I, which can be rewritten as C V tensor W. Okay, but that's exactly one of the conditions that we wanted to impose in our final structure. We wanted to be able to move scalars from one component to the other and outside of both components. And we just checked that we could move it from the first component outside of each component. Okay, so let's maybe get a couple of homework exercises that look like this on the board, and then we'll dive into an example. So as a nice homework exercise to understand this structure via the quotient vector space, it might be nice to prove the following 3 identities hold. So this is that V tensor CW is the same thing as C times V tensor W. Then we've got some sort of distributive rule. So V1 plus V2, where V1 and V2 are both in V. Tensor W is the same thing as V1 tensor W plus V2 tensor W. And then finally, we've got another thing that looks like a distributive rule, but in the second component. So like I said, if you've never played around with this structure of a quotient vector space, it's useful to write these down at least once. Now that we've got this construction taken care of, let's look a little bit at the proof of a certain basis for a quotient vector space. We won't look at all of the details, but we'll look at half of the details. Now we've got a theorem about the basis of the tensor product of two vector spaces. We're going to look at the finite dimensional case here, but you could also do something similar for the infinite dimensional case. So let's suppose that vector space V has a basis of m vectors given by V1, V2, all the way up to Vm. And then vector space W has a basis of n vectors, W1, W2, up to Wn. Then the basis for vector space V tensor W will be Vi tensor Wj as I runs through all possibilities for I, that is 1 through m, and j runs from 1 to n. So this includes things like V1 tensor W1, V1 tensor W2, V1 tensor W3, V2 tensor W1, and then so on and so forth. So an immediate result from this is that the dimension of V tensor W is the product of the dimension of V with the dimension of W. So let's maybe compare that to the dimension of V plus W, the direct sum, which is equal to the dimension of V plus the dimension of W. So now after this, we've got two ways of combining vector spaces, a direct sum and a tensor product. And what's nice is that the direct sum will add the dimensions, whereas the tensor product multiplies the dimensions. So I think that's nice, a nice holistic view of these two kind of things. This is a generalization of addition, but for vector spaces. And this is a generalization of multiplication, but for vector spaces. Okay, so let's dive into the proof of this theorem, but we'll only prove the spanning. We will not prove the linear independence, which is a bit trickier, and we might do that later if there is interest. So let's recall that every element of the tensor W is a finite linear combination of elements of the form little v tensor little w with little v in v and little w in w. Now notice I did not say that every element of V tensor W was of this form. I said every element of V is a finite linear combination of elements of these forms. This is called a simple tensor, and every element of a tensor product is a linear combination of simple tensors. And that comes from the definition of this tensor product via the quotient of the formal product like we've seen. Okay, but the thing is if we can show that this thing right here can be written as a linear combination of guys in here, then we're good to go because we can just reshuffle all the sums around in the end. Okay, so let's use the fact that V is in V and W is in W to write the following. So we can write V is equal to A1 V1 plus all the way up to AM VM. And then we can write W equals B1 W1 plus all the way up to Bn Wn. Again, that's because we've got a basis for vector space V and a basis for vector space W, and V is in V and W is in W. So now we can take V tensor W. So this is going to be the sum as J goes from 1 up to M of AJ VJ tensor W. So I haven't really done anything here. I've just replaced V with its form expanded in our basis of V. Now I can apply those conditions which I imposed on the tensor product via that quotient to distribute this tensor W inside of this sum. So that's going to give us something like this. So we'll have the sum as J goes from 1 up to M of AJ times VJ tensor W. Now we're going to take W and expand it using this form, given that we know a basis for W. So that's going to give us the sum as J goes from 1 up to M of AJ, and then we have V tensor. Now we have the sum as K goes from 1 up to N of BKWK. And again, I can use our conditions, which we imposed on the tensor product, to pull this sum outside of the entire thing and pull these coefficients out of the entire thing. And that's going to give us something like this. So we'll have the sum as J goes from 1 up to M, and then the sum as K goes from 1 up to N of AJ times BK times VJ tensor WK. But that's exactly where we needed to end up to finish this spanning argument. Okay, now that we've got this taken care of, let's look at a concrete example. So let's finish this off with a fairly simple example, and that will be a basis for R2 tensor R3. So as we saw before, R2 is 2-dimensional and R3 is 3-dimensional, which means the tensor product should be 6-dimensional, 2 times 3. And also, we know a basis for this will just be the tensor product of basis vectors from here with basis vectors from here. Okay, so let's get started. So our first basis vector will be of the form 1, 0, tensor 1, 0, 0. Okay, and then our second one will be of the form 1, 0, tensor 0, 1, 0. And then finally, our last one will be 1, 0, tensor 0, 0, 1. So those are our three basis vectors built off of this first basis vector for R2. And then we've got three more built off of the second basis vector for R2. So we've got like 0, 1, tensor 1, 0, 0. And then 0, 1, tensor 0, 1, 0. And then 0, 1, tensor 0, 0, 1. So there's our total of 6 basis vectors for R2 tensor R3. And now I'd like to point out that there's another vector space which is naturally 6-dimensional, and that would be the vector space of 2 by 3 matrices. And in fact, there's a nice way of matching these basis vectors with basis vectors for the vector space of 2 by 3 matrices. So this vector will play the role of 1, 0, 0, 0, 0, 0. So that matrix, and then this one will play the role of 0, 1, 0, 0, 0, 0. This one will be 0, 0, 1, 0, 0, 0. And then you can see where we're going from there. So this one will be 0, 0, 0, 1, 0, 0. This one 0, 0, 0, 0, 1, 0. And then finally 0, 0, 0, 0, 0, 1. So there's a relation between basis vectors for M2 by 3 and basis vectors for R2 cross R3. And since when we're dealing with vector spaces, the only thing that we need for an isomorphism is an equality of dimension, what we clearly have here is R2 tensor R3 is isomorphic to M2 by 3 with entries in R, which in turn is isomorphic to R6 because that's also 6-dimensional. But maybe I'll put this one in parentheses because this isn't quite as natural as our first isomorphism. Okay, so let me know in the comments if you'd like more takes on the tensor product from slightly different points of view, and that's a good place to stop.